So hi everyone, and welcome to the MLOps Live webinar series. My name is Sahar and I'm the VP of Marketing at Iguazio. It's great to have you all with us today. This webinar series is dedicated to operationalizing machine learning and bringing data science into real business applications. And today, we're going to be demonstrating how to handle large data sets in data prep and training. This is often viewed as a daunting task by practitioners, but it doesn't have to be. There are open source tools that can help you work with data at scale in a simple and reproducible way. But before we dive in, I'd like to invite you to join our MLOps Live community on Slack so that you can ask us any questions after the session and let us know if you run into any issues when you're working on your ML projects. There are already over 200 members in our community who support each other on MLOps related issues. We'll drop the link in the chat box for you now. And now on to the main event. This session today will be presented by Iguazio's co-founder and CTO, Yaron Haviv, a serial entrepreneur who served in multiple CTO roles before starting Iguazio. Yaron is also the creator of MLRun, Iguazio's open source end-to-end MLOps framework, and Nucleo, Iguazio's open source serverless technology, which has over 3,400 GitHub stars and is widely used. He will be joined by Idan Benun, data scientist at Iguazio. Idan has led information-rich projects in energy, healthcare, and finance, and has extensive experience with use cases involving large-scale data, such as money laundering and fraud prevention. Idan will be taking us through some in-depth live demos today. We'll get started with an intro to MLOps, then look at a comparison of open-source tools available for large-scale data processing in Python. We'll then show an intro demo to Dask and discuss running Dask over Kubernetes with MLRun for elastic scaling. Then we'll finish off with an in-depth demo on deploying Dask-based data engineering and ML pipelines with MLRun and Kubeflow. And we'll make sure to leave plenty of time to answer any questions you might have, so feel free to type your questions in the Q&A panel at the bottom of your screen during the presentation. We'll also be running a short 2-question poll, and we're very interested to hear from your experience, so do please fill that in. These polls help us make these sessions as valuable as possible for you. As always, we'll make sure to share the poll results at the end. We've now put everyone on mute, and we're recording the session so that we can send it to you afterwards. And now I'll hand things over to Yaron to get us started.
So thank you, Sar. So just a couple of slides intro before we dive into Idan's presentation and demo next. So we know that part of the biggest challenge today in ML and AI is the productization and operationalization phase, where you have a research environment and then you essentially have to refactor everything for dealing with production pipelines that handle data at scale, data that derives from multiple sources, running training at scale. So the word scale is sort of repeating itself when it comes to production sites. And this is really where we want to take this presentation and this demo to understand what are the options that someone has in order to process data at scale for data preparation and for analytics. And that will be the focus of this week's discussion. Next slide, please. So, one of the things that we keep on talking about is what does it take to operationalize any piece of code in data science and analytics in order to get it to production. So obviously you have the coding part, but then you have the packaging part. You have to, make it sort of a containerized, etc. And then you have the two aspects that will be the focus of this discussion today is how do you take something that works within your notebook, small scale, and how do you scale it out? How to make it perform. And these are all those techniques that some of those frameworks that we're going to talk about are using, data partitioning and distribution, etc., along with parallelism and other techniques of caching and paging. So this will be what we'll focus on today. And we'll also show how it's tied into the overall frameworks to allow automation and CI/CD and sort of zero effort from the data science part. Next. So again, if we look into a pipeline of machine learning, it essentially has several key elements. One, you need to bring in all the data. and that will be done through ETL jobs or streaming jobs. Then you need, once you've placed everything in sort of a storage layer or a feature store, you need to start preparing the data and make it ready for training. Once you do that, you need, again, to do the training at scale. And once you have a model, you need to think about how to deploy that model, manage and monitor that model. So that is the full life cycle. And we're going to focus this time on the scaling of the data preparation and the scaling of the machine learning pipeline. Okay, so with that, we'll move into Idan's part. And Sarah, back to you.
Thank you, Sarah. So I think in some point in our work, we all get into a point that we need to handle large data sets. And obviously, when you work on a pipeline, on a machine learning pipeline, you need to handle the main 4 elements in the left side of the screen, which is exploratory data analysis, feature engineering, train, test, evaluate. I put it in one place because it's related. And things that related to versioning and monitoring the pipeline itself. In most of the time, when you try to scale this element, one of these elements to large data sets, you have different problems in every, or different challenges in every element. When you do exploratory data analysis on a big data set, sometimes it can take time until you get a basic answer of statistical information that you want to gain on your data frame. When you do a feature engineering, if the feature is quite complex, when you move to large data sets, the pain is growing, okay? So it will be harder to generate the feature that you actually want to generate on a larger data set. And it's even getting more challenging when you try to train a model, a machine learning model, or a deep learning model on a big data set. Sometimes, of course, you don't need to train on a very big data frame or data set. But in I would say a lot of cases, you do have the need to scale your training process. And in most of the time, this is one of the pain points in the pipeline when you try to scale your training after you generated all the features and did your exploratory data analysis. And obviously, versioning and monitoring, for example, versioning, you want to keep versions of your datasets or your feature while doing or building the machine learning pipeline. So all of those elements, you want to do them in low latency. Obviously, you want to get your answers fast, relatively fast. It depends on what you work and if you need it. You want to be able to scale from 1 million rows to 1 billion, and if you need to, a few billions or more. You want to be able to integrate with other part of your systems. Sometimes it doesn't end up with the pipeline. Sometimes you need to connect to other elements of your system or your business applications, and you want to be able to do that on a large data set. Obviously, everything here is trained on machines, and you want to make sure that when you scale, you have an efficient computation abilities to make sure that you are actually utilizing the hardware that you have in place. One very important point is the fault tolerant. Basically, when you build a machine learning pipeline, there is a lot of points that you can fail in the pipeline, and you want to be able to go back to the last point that you failed and continue from there. On the larger data sets, it's sometimes even harder. I think that the last point is the most challenging one, especially when I did some work on batch processing for fraud detection or money laundering detection. When we try to move from batch processing to real-time processing, you face a lot of challenges that related to any element on the left side of the screen. For example, feature engineering can be very different story when you try to build features for batch processing and try to build features for real-time processing. So I think that that's summarized in high level the challenge. Next. So there are a lot of frameworks that can handle large-scale data sets. We chose to focus on those three, VAX, Spark, and Dask. Obviously, there are frameworks like Ray and QDF and things like that that's worth mentioning, of course, but let's focus on those three. I will go over the core technology in high level and some more elements in this table. VAX is actually using something that's called memory mapping. Maybe before I jump to the core technology, I would say that VAX was actually developed by a group of scientists that wanted to investigate and analyze exoplanet data, data that comes from large telescopes that explore the space. And it's basically a high-performance Python library for lazy out-of-core data frame, and I will explain in a minute what it means. And the purpose that was the main game here for the guys who developed that was to actually visualize and explore big data sets on one single machine. So let's keep it in mind. They are using something that's called memory mapping. What is memory mapping? Is actually a mechanism that maps a portion of a file or the entire file to a disk and to a range of addresses that actually can be accessed by the application that you are using. And by that, actually allowing you to do some fast operations. The zero memory copy is actually talking about or describing a computer operation that the CPU does not perform the task of copying data from one place to another in the memory, and by that saving some CPU cycles and memory bandwidth when you try to transmit a file over a network or between the disk and the memory. Lazy computation is an element that you will see in Spark and Dask as well. It's actually saying that you call it when you need it. It's a strategy which actually delay the evaluation of an expression until the value is actually needed. And also by that, avoiding by repeated evaluation that sometimes happen in a code that you are developing. In terms of API, I would say that VAX is about 30 to 35% similar to Pandas, which is nice and help doing the ramp up when using VAX. I think that the main drawback of VAX is the fact that you can gain the real speed of VAX only when using a file format that's called HDF5, which is basically a file format that uses hierarchical mapping, which allows it to actually access part of the files in very high speed. So obviously, when we talk about scale, most of the examples that you will see online will talk about the taxi, New York taxi dataset, which is about 100 gigabytes. And VAX is doing a really good job on a single machine, a laptop, a strong laptop, I would say. And by processing that and get some statistics and visualizations. When we talk about machine learning, if you really want to scale out of memory, it means that you really want to train with VAX on a file that is bigger than your memory. You have only two options. One is to use estimators or algorithms that have something that's called partial fit. It means that you can train a model in batches. Obviously, not all the machine learning models have this ability, so you're limited to the ones that actually have this ability. And the second option is to use one of the estimators from the API that VAX has. VAX has an API that's called the VAX-ML that actually holds few additional algorithms on top of the one that using partial fit methods. If we will jump to the next framework, I think that most of you will be familiar with Spark. I would say it's the oldest guy in the pack. And the core technology, maybe before, Spark is basically an open source general purpose cluster computing framework that's actually was developed in the University of California, and today it's maintained by the Apache Software Foundation. In terms of code technology, Spark is using really in high level again, using something that's called this distributed task dispatching, which means that it will take your code, it will break it down to small tasks, and actually dispatch the task to the different workers or the different machines that you have. Obviously, Spark is dedicated to distributed systems. When you have multiple machines, you can work on one node, but it's not the purpose of Spark, basically. So after breaking down the code that you are trying to run into small tasks, Spark will start the scheduling process, which is basically a mechanism that decide when to do what and how to plan it in terms of time. And together with some I/O functionalities, Spark is pretty good in processing a lot of data. In terms of API, when you want to write in Spark, you have two options, to write in Scala or in PySpark. Today, we also have something that's called Koalas, but it's pretty new. But till not far ago, if you wanted to write in Spark, you had quite a learning curve to do. In terms of files, Spark can handle all the file formats, or most of them, I would say. CSV, Parquet, HDF5. Obviously, on Parquet, for example, the performance will be a bit better, and that's it in high level. In terms of scale, it's actually a function of computing power. As you have more computing power and you are not limited by any disk bounds or things like that, you have the ability to scale and train a lot of data with Spark. Also, nice thing about Spark is that it has its own parallelized algorithms built in within the API. Some classification, regression, clustering algorithms that are part of the Spark API. Obviously, not all the machine learning algorithms are there, but most of them, I would say. Okay, I will jump into Dask. In terms of Dask, core technology, maybe before that, I would say that it's also an open source library for parallel computing with Python, which is the difference from the big difference from Spark. It's very similar to Pandas and other elements like NumPy and things like that that make it easier to interact with it. And it's a community project that is actually maintained and sponsored by developers and an organization. In terms of core technology, it's very similar to Spark, so I will not go over it again. In terms of API, as I mentioned, very similar to Pandas, which make the learning curve quite easy. In terms of file, also can process all kinds of files, and also in terms of scale, a function of computing power. To scale out of memory, just like in VAX, you need to use partial fit methods, algorithms that can scale, algorithms that can be trained in batches, or to use one of the estimators that Dask has. For example, XGBoost is something that includes in the Dask ML library. Next. Yaron, something to add? Okay, cool. Really quick benchmark. There is a really good source. There are a lot of blog posts, great blog posts that talk about the benchmark between VAX, Spark, and Dask. This one, which you have the link inside, is actually taking the taxi dataset and working on one single machine, which is pretty powerful. And what we see in the chart is seconds per task, and obviously lower is better. You can see that the tasks that are performed here are not related to machine learning, but more to, I would say, feature engineering and exploratory data analysis. And VAX is pretty fast in doing those. And remember, is doing that in this speed only with HDF5 files. It's also give you the ability to convert from different formats, but again, it's a real drawback because most of the files that we are working on are Parquet, or at least myself, Parquet or CSVs. You can see that Spark is somewhere in the middle and Dask is last, but remember that when you work with Spark and Dask, you need to work on multiple node environments to gain the power of those frameworks, which is not the case here on a single machine. Obviously, it can parallelize on threads and processes. We'll talk about it in a minute. Next one. Next slide, please. Thank you. Okay, so when to consider what? So as we mentioned, when you need to work with large data set on a single machine in HDF5 file formats, VAX will be a great choice. When you work on involves visualizations and plots of large data sets, also great, VAX can be a great choice. And it's actually what it meant to be. So easy to go to that. Next one.
For example, so Idan, that means that if you want to load the file once, because most people don't use HD5, they will use like a Parquet or a CSV or a database to store the data, then essentially, if you only do one pass on the data, just to query all the data, probably it won't be efficient. But if you have the time to convert it to HD5, store it in an optimized fashion, and then you want to do multiple iterations on the same data, like group, join, clean, etc., then it will make more sense. It sounds more like a data exploration kind of workload, not like a real-time pipeline or something like that.
Definitely, and the creators of VAX also saying that this is the purpose of it. So if you will go to the GitHub page of VAX, you will see that this is the first paragraph that talks about that.
Great.
And when it comes to Spark, if you prefer a more SQL-oriented language, Spark can be interacted with SQL API. And when you have mostly JVM infrastructure and legacy systems, you will see Spark in a lot of big enterprises because it's relatively old to the other ones. Definitely Spark can be a choice. When you want to establish a trusted solution for your business, sometimes banks using Spark in terms of fault tolerant, Spark can do a good job. When you're mostly running business analytics with some lightweight machine learning, when you want to scale to different or more heavy machine learning operations, Spark will not always have the answer. Definitely Spark has its respects, but it really depends on your need.
All right, so also going back to Spark, so its origins is more in analytics space. And that's also how its architecture works, like with RDDs and all of that. So if you're trying to do like SQL and analytics workloads, even working with Kafka or different data sources, it's a good choice. But the problem is really that it's not native Python. So if you like using Python tools, every time you move to Spark, you have to essentially convert your entire data set from like a pandas data set into like a Spark data set. And you can't use Python operators on the data. Same for machine learning workloads. If you want to use all the machine learning stack of Python against Spark data, that's pretty challenging. And machine learning libraries within Spark are not necessarily up to date.
Definitely, and I can also give an example on a real challenge that I had with Spark. For example, I wanted to perform some operation that called SMOTE, actually handling imbalanced data sets in machine learning problem. And actually, I had to write my own SMOTE function when in Python you have it in one line. So it's pretty limiting you when you try to do some basics operations when building a machine learning solution.
So that leaves us with the Dask. So.
Definitely. If you prefer, like Yaron mentioned, if you prefer Python or native code and you don't want to rewrite your code or invent the wheel, I would say, on a simple operation that already built in Python, definitely Dask can be your choice. The fact that it can integrate with all the Python libraries and other elements make the life much easier based on what I saw. When you use complex, when your use case is complex or does not fit into Spark computational model, sometimes you actually can do things in Spark due to the fact or due to the limitation of how it's working. It's not common, but it's there. I had the chance to encounter these issues. Definitely Dask can overcome that. When you actually want a lighter weight transition from local computer to cluster computing, and we will see an example to that later on in the demo. I think one of the most important things is if you want to interoperate with other technologies, Dask will be the answer. Anything to add, Yaron?
No.
Okay, so let's take a dive into Dask architecture. I will try to do it easy and fast. Basically, you have three elements. On the left side, I'm talking on the left side, a graph or chart of the screen. You have three main elements. You have collections, task, graph, and schedulers. The collections are the front-facing APIs that you work with. You can work with Dask Array, which is very simple, very similar to NumPy Array, Dask Data Frame, similar to Pandas, Dask Back, delayed features, which is additional features of Dask. What collections are doing is actually creating a task graph. A task graph is actually a manifest or a recipe that's actually define how you want to perform your task or your code in a parallelized way. Then the task graph go to the schedulers, which actually execute the task graph and actually decide when to do what and for how much time. When you work on a single machine, the scheduler will work with thread processes. When you work on a distributed machine, it will do it on a multiple machine or multiple workers. The right side chart is actually showing you how it's done in high level. based on something that's called blocked algorithm. If we take a NumPy array and we want to summarize it, we do .sum and we get the sum of the array. But when you work with the big array, what Dask will do is actually break it down to two chunks. You can see chunk 0 and chunk 1. He will separately calculate the sum of every chunk. Sometimes it can actually do it on different workers, and by that actually parallelize the work. Sum every chunk, and then sum all the array and get you the answer as a whole. Next. When you talk about Dask distributed, it's actually working in a way that you have a client, which is the user face point, usually Jupyter Notebook or your favorite IDE. The scheduler is actually manage the state and send the task to the workers for execution. Like we mentioned, the scheduler take your collection or the task graph and split the work between the workers, between the different machines that you have available, compute the task, store it, and actually serve the computed results to you, back to you. Anything to add here, Yaron?
No.
Okay, cool. So let's see a quick demo. First, I will show some and we'll show how easy it is to move from regular Python to Dask operation, distributed operation. I'm just importing some libraries that we will need it, setting some paths for the data, calling or initiating the Dask client, and initiating a Spark session. What I will do here, I will read the data, and then I will call head, which will show me the first few lines of the data. The reason I'm doing that is because it's Vax and the other frameworks are lazy. If I will not do anything that actually require the answer, it will do nothing. Okay. So if we will do it with Vax, we will see it will take 1.8 seconds. If we will do the same thing with Dask. Let's see. Why not showing the results? Yeah, no. Okay. With Spark, it will take a bit longer. It will take about 2.5 seconds. And we did the same operation and we saw the differences. In this case, Dask is the winner, but remember that once you load the data into Vax, it has some advantage. And when you do a simple group by on a column and count the number of rows in the dataset, Vax is pretty good at statistical operations and visualizations. When you do it with Dask, it's also pretty fast, about 1.2 seconds. And when you do it with Spark, it's a bit longer, 1.2. Now, the nice thing about Dask is how easy it is to move from a Python function and parallelize it on multiple workers on a distributed system, which is not an easy task if you want to do it in Spark, for example. What I'm doing here is just importing some libraries. I will not generate the files again. What I'm doing here is actually generate random files with random letters. I'm actually generating 100 files that every file is actually 10 megabytes. And then what I want to do is to count sort and count the letters in every file and get back the answer. We can see that the operation with a simple Python will take about 2 minutes and 30 seconds. All I'm getting back is the number of letters in the file, and for the 100 files that we have. And once we do that with Dask, the only difference is I need to obviously I need to initiate Dask client. I'm actually mapping the file or getting all the path for all the files in the folders and taking my function, the same function that I use, count letters, that's actually also sorting the file, and I map it to every path in the list that I have, and basically doing the same, just parallelized in maybe 2 lines of codes, will give me the same results in 25 seconds, which is about 6 times faster, which is, for my opinion, very nice thing. This was a quick demo. We'll get back to that when we talk about the pipe.
Okay, so we saw how we can use Dask, and it's actually pretty useful when it comes to just taking your Python code. And I've spoken to some of our customers in Iguazio, and which moved from Spark to Dask. They told me it's essentially bringing a lot of velocity to their data science team, that instead of doing every data engineer calling every data engineering task, calling a data engineer to redo it in Scala or PySpark, essentially the data scientists themselves are building stuff and it just scales. So I think it's very valuable. The problem is that when you need to build Dask beyond a single machine, you want to scale it on a cluster. And the best way to scale it on a cluster is using Kubernetes. And you essentially need to have this Dask, which is a distributed architecture that have multiple components. It has the workers, the schedulers, the client, and potentially other elements if you want to access Dask cluster outside of the cluster. You need to install all of those as containers on the Kubernetes cluster. So that's the first thing. Everything in the Dask cluster needs to be orchestrated and running in that cluster. It's one of the neat features of the Dask Kubernetes integration is auto scaling. So you can essentially build it with 0 workers. The scheduler will get some workload and it will start expanding, and you can define what is the minimum and maximum amount of workers that you want to have. So this way, not just go and scale it to 100 machines and pay the bill in Amazon later. So you have a control over auto scaling, and on one end have dynamic scaling, on the other end be able to control that. What is the challenge around it is that when you want to run a workload in Dask, it's distributed across 3 different components: the client, the scheduler, and the worker. So if, for example, you're using some package, let's say scikit-learn, the scikit-learn package has to be installed with exactly the same version. And we've seen the problem, what happens when it's not the same version, it just doesn't work. You have to make sure that you have exactly the same versions of packages in all those 3 different components. So when you're orchestrating the cluster, you have to make sure that you build all the packages and all that identically in the different elements. Another critical thing is that, just to take the example that Idan showed of running some sort of word count on a bunch of files in the cluster, all the workers have to have access to the same files, because you don't really know which worker is going to access which file. So you have to have some sort of a cluster file system that connects all those workers together, or an object store, but that may add an overhead of sort of copying data locally. But you have to have sort of a shared storage media that all those workers, or shared file system that all those storage workers can access. And if you can have sort of shared data frame semantic, like we do in sort of Iguazio, it's even better. Then it really allows you working with bigger data. And the other point that you see here is that you may want to access the cluster externally. So in this case, you would need some sort of API gateways and credentials that will allow you to access have a client that submits jobs to the Dask clusters from your laptop, for example, or even access the Dask UI. Dask has a pretty cool UI, and Idan is going to show you that in a minute, where you can actually see the progress of your jobs, the allocations of memory, and all of that. And that's what you see here is relatively challenging. You have to go in and build all of those containers and manage their life cycle. There's no real life cycle management in Dask over Kubernetes. So someone needs to essentially build the containers, tear them down, monitor their activity, etc. Going to the next slide, Sar. So one of the things that we've done in Iguazio, that part of our one of our open source projects called MLRun, is essentially a framework that has many different attributes. You know, it has the serverless runtime objects, it's a model tracking, model monitoring, model serving, feature store, and many other components. But the runtime element within MLRun is a framework that makes different runtimes like Spark or Dask or deep learning jobs around Horvath. They make it look like a serverless job. Essentially, you just submit some code. All those containers and all those configurations and packages, they're essentially built for you. There's also sort of an automated lifecycle management built around it. So you can just take a piece of code from your notebook and submit it to the MLRun controller, and that will build all those resources for you. You know, the containers, the file mounts, the monitoring, all those aspects. In some frameworks, MLRun actually knows how to create parallelism and deliver much higher performance. That's with Nucleo, that's very evident. You know, you can take a piece of Python code and it will run in parallel much faster. Another element is that you can essentially write some of those functions and put them in a marketplace. And then as you build pipelines, like Idan will show in a minute, you can just drag and drop. So let's assume you have a training job and a validation job and maybe a data preparation job. You can write them once and then just drag and drop them into a pipeline and build a full pipeline where combination of Dask or Spark or other runtimes are used. And part of the other thing that MLRun does is the ability to work in a scalable fashion, but essentially integrating a distributed messaging layer, like in the case of Dask or MPI in the case of deep learning, or the Spark RDDs and data frame in the case of Spark, and couple it with a distributed data layer. So you can essentially run the same workload seamlessly without having all those data related issues that we just discussed, that one worker will not have access to the data. There are also aspects here of security and access control that are maintained. So we can now build those scalable workloads that seems like an individual workload running on individual runtime. So with all of that, we're going to see now a more advanced demo of how to essentially leverage MLRun for the automation or making Dask serverless, and Kubeflow is a way to build pipelines of those individual steps.
Okay, so what we'll do now is actually build this pipeline that we just talked about. And we will start by calling some libraries, define the project with MLRun, actually given the project name, and define the project dir directory, and actually setting up the environment for the process. So we run this cell. I already initiated a Dask cluster, so I will not do it again. But basically what we do here in a very simple line, by calling a new function, which is a kind of Dask. And I'm also giving it an image that holds all the requirements, packages that I need for the process that I will build in the next cells. I'm also defining the Dask cluster itself, how many replicas I want, how many workers basically, how many, what is the memory I want to allocate for every worker, and the number of threads. So you can see it's quite easy to define the specification for the Dask function. Then we save the function. And Yaron mentioned one of the limitations of while not using MLRun is actually get the shared access files between the client and the workers. And this is actually solved by running this line, which actually mounting V3IO to the Dask cluster.
Maybe just to expand the concept again, we have an object that represents the Dask cluster. We call it the Dask function. We can have, by the way, the same thing for Spark and Horvath and many other frameworks or just our job. And when we create that function, we could give it attributes like the size, do we need GPUs or CPUs and memory, threads, all sorts of parameters that every runtime has. Like, for example, in Spark, you may need jars and some other things. For Horvath, for deep learning, there may be other requirements. So every function runtime has those unique attributes. And here we're setting those unique attributes. There are common attributes, like you want to mount a file system, like in this case, the Iguazio real-time V3IO data layer. Then you just do a mount V3IO. You can also mount a PVC volume, if you're familiar with Kubernetes, or other forms of storage into those functions. And then this function, by just calling its client, is essentially you're getting the endpoint, the access to that Dask cluster, and you can use it later on in your application. Yes, Idan, you can continue.
Thank you, Aaron. So as I mentioned, by calling the Dask function .client, I'm initiating the cluster, and you can see that I get a link to the dashboard. You can see that we get the address that we can use for calling or using the Dask cluster, the scheduler address that we mentioned in the presentation before, that actually manage all the tasks. And then once we initiate the Dask cluster, we setting up the functions that we will use in the pipeline. You can see that setting up a function is quite simple, very similar to how we set the Dask function, that just this time the kind will be different. It's a job, and we also given it an image that holds all the things that we need in order to run this script that I will show you in a minute. We have two functions here that actually can become also serverless functions. One function is pretty simple, just calling describe, simple describe on the dataset, getting some statistics and saving it. The second one is a bit longer, actually running, giving you the ability to train a model with any sklearn algorithm that you want. Those functions are defined in a simple Python script that we are calling. The first one is describe. You can see that I'm initiating, calling obviously some libraries, calling the context of MLRun, and basically using the Dask address or the Dask client to initiate it or use it. So to use it during the process, running the describe and actually computing the results. The next function that we mentioned was the train model function. It's a bit long. We will not go on every detail here, but basically you get a data set, you set in the models that you want to use, the parameters, the hyperparameters for the model that you're using, the destination of the artifact, if you want to drop some columns, if you have a label column, you need to mention it, how you want to split between train and test, and so on. But basically, over here, it's a Python code. It's very similar to what you use to do in Python. Sometimes you will see points that I'm calling things that related to Dask, like compute or things like that, or to Dask array. But most of the code is very similar to what you are familiar with. By the way, if you want to use scikit-learn models that are not part of the Dask ML API, you can use joblib with parallel bake and Dask and call any algorithms that you want to use. So if we will go back to the creating the pipeline, over here we define our functions. Over here we define our pipeline. Obviously, we start with some parameters with the labels that we have in the data. I'm using a subset of the yellow taxi trip data. Also given it the Dask client address, the scheduler address that we initiated before. And then we define the functions that we want to have within the pipeline. The first one is describe. We give in to the function the parameters, basically the datasets, dataset, and then we want to run our Dask sklearn Dask classifier, which do the training, the testing, and evaluation. Specifically here, we call random forest classifier. We're giving it some params, and we set the pipeline. So let's run this. Then we basically set the workflow by saving it to a file as well, and saving everything into context. Now let's run it. We actually, you can see that what's doing MLRun doing nicely is giving you the ability to access the data, if it's Dask dashboard or the pipeline itself. We'll jump into the pipeline and we will see it in action. Sorry for the low weak connection. Okay, so over here I have a few pipelines that I ran before. If we will go into the pipeline that's actually running, we can see that the describe function is already done, and we have the results. We initiated Dask, we got the Dask addresses, and we read the data and run the task that we wanted. Now we are training the random forest classifier. This operation will take about 4 minutes. If we will jump to the dashboard, we will see the Dask cluster in action. What we built, the trees are getting built in parallelized way using Dask. All those operations that happen in the background are actually parallelizing our algorithm nicely. And it's obviously you can jump between the status, the usage of the workers. You can get some more information about how it's performing the task and so on. Eventually, let's wait a few minutes, but eventually you will get the results here according to what you defined in the script or in your function. For example, I defined for MLRun context to the fact that I want to log the dataset that is actually generated from the describe function. Actually holds all the statistics for every column. I want to log the dataset, so eventually once the pipeline is finished, we'll see it in the outcomes and we will be able to access it throughout MLRun UI. Let's wait a few minutes. Same thing goes for all the results that we have from the scikit-learn classifier. We can save the model itself. We can save the scaling mechanism if we have some in the training process, the label encoders and so on, also the log datasets, and obviously the matrices, the AUC, the accuracy, the recall, and so on. Yaron, anything to add? While we're waiting, I already have some Let's see how much time we are running. We'll finish in a minute.
Anyway, what we've seen.
While we're waiting, we can jump to the MLRun UI. Go ahead.
No, I'm saying that what we've seen is that we can automatically provision Dask cluster, and then we can run a pipeline with multiple steps on the same Dask cluster. Later on, we can let it die. It essentially dies after a certain timeout that you've specified, or we can just kill it if we don't need the resources. So you have elastic scaling of your workloads. I don't know if you've shown the Dask dashboard and how.
Yeah, it's shown.
Yeah, sure. So you can see that you can build those pipelines, you can monitor them, and you can also integrate them through the kubeflow pipeline mechanism with other engines like Spark or just regular jobs or Nucleo functions or any other runtime supported by MLRun.
So in terms of results, we can see if we will go to the Dask classifier training model process. By the way, I can see that it just finished the process. Over here, we will get the output of the functions that we ran in the pipeline. We get all the matrices per class. It's something that you can define. You can define it differently, obviously, and all the artifacts. We are generating all the at the end of the training process. If it's ROC, classification report, confusion matrix, and so on. If we will go to the MLRun UI, we will actually be able to see it. For example, the ROC. Let's refresh the page here. Let's do that. And go to the job that we ran. If we go to the artifacts, we will see all the charts that we have. If it's the ROC, if it's the classification report, and all the other elements that we have that you want to save into the artifact area or database. We can also see the results, the precision for every class, the recall for every class, the F1 score, and so on. And basically, that's it.
And we did want to take two questions, two quick ones, and then we'll wrap up. So the first question that we had was, how do you share data among the Dask users? And is there a way to control data access like in Spark?
Yeah, so actually it depends how you're using the data. You know, if you're using object store, then you would use, object store credentials. If you're using a file system, there is sort of a challenge. If all the workers are using the same file system mount, then it could be problematic. The same access will be to everyone using the same cluster. In Iguazi, we have some tricks around it. The Victor.io file system has a special plugin that allows each user to essentially submit using his own access key. So every user could be limited to a specific area in the file system.
Excellent. And another question that we have here is about serving models. If you can say a couple words about how you serve models.
So when you build those models with Dask or any other framework, you generate sort of those model files. You have Nucleo serving or MLRun serving, we call it sometimes, which is an engine that could just take a model object or a model file and convert it into a real-time serving pipeline, including all the drift analysis, etc.
And we'll just take one last one. I am new to machine learning. What is batch fitting and what ML algorithm supports it?
Can you repeat the question?
What is batch fitting and what ML algorithm supports it?
Okay, so you can go into scikit-learn website and see and actually search for algorithms that have the partial fit methods. It means that it can actually do the calculation of the algorithms in a batch processes. Not all the algorithms allow this option. For example, things like clustering are more easy to do partial calculation or a partial fit process. And then even if your data is bigger than memory, you can work with it.
Excellent. And we are out of time, so we don't have time to take any more questions, but we do invite you to join our Slack channel, and we can keep answering your questions there. We'll be happy to continue the conversation. Before we drop off, we did want to invite you to visit our MLOps page on the Iguazio website and learn more about bringing data science to production. On this page, you can find previous sessions of this webinar series, as well as blogs, videos, and other resources on simplifying your path to production. Here, practitioners from Netflix, Twitter, Microsoft, GitHub, and many more leading companies shared their advice on operationalizing machine learning, and it's all there for you to enjoy. We'll go quickly to the poll results as promised. So the first question, poll question was, how do you handle data prep and training on large data sets in your organization? And most of you are still actively looking for a good solution, which isn't surprising considering what we've just heard here today. The second poll was about which tools you're using to build your data and machine learning pipelines today. And again, most of you are looking for a good solution there. 24% are using Kubeflow or Argo, 21% Airflow, and the rest are using other solutions here. Okay, well, this concludes today's session. Again, we invite you to continue chatting with us on our Slack channel. And at this point, I wanted to thank Yaron and Idan very much for a great presentation. And thanks everyone for joining in and for staying with us, even though we went a couple minutes over time. We hope you enjoyed it and found it useful.